Hello everyone, thank you for being here today. We're excited to present you our design project on landing gears for ARO 2311, which is a class of elements of avionics. My name is Aaron Dutt, and I'm joined by my talented group members Reyes Cabral, Savannah Jomo, Diego Urias, Daniel Panamano, Justin Millsap, Matthew Portugal, and Tobin Buenaventura. Our presentation will follow the following outline. In the introduction, we will give you some background information about our project. We will discuss the assumptions we made, the theories we applied, and explain the significance of our work. Furthermore, we will outline the main goals we set out to accomplish. In Design Overview, this section will provide a summary of our project, including the design process we followed and the goals we aim to achieve. In the analysis section is where we delve into the research we conducted for our project. We will discuss the requirements we identified and provide a thorough discussion of our design. This part will give you insights into our decision-making process and the rationale behind our design choices. In the construction section, we will discuss the implementation of our design. We will walk you through the stages of construction and highlight any significant aspects of the implementation process. This section will give you a closer look at how we brought our design to life. In the conclusion, as we wrap up our presentation, we'll provide a summary of key points covered throughout our presentation. We will also discuss how we verified the requirements and present the final takeaway from our project. Finally, we have included an appendix that contains additional details such as calculations, codes, truth tables, graphs, and any other relevant information. This appendix serves as a supplementary resource for those who are interested in a more in-depth exploration of our work. Since I have told you our outline, now let's move on to the next part of our presentation, the introduction. In this section, we'll provide you with the background information, assumptions, theories applied, and discuss the significance of our project. This is where we lay the foundation of our project and give you a comprehensive understanding of its context. Let's start by providing you with some background information and setting the stage for what's to come. Our project focuses on the design and construction of a simple aerospace-related mechatronic device known as the landing gear. As we all know, landing gears play a critical role in enabling an aircraft to safely land and take off from the ground. Before we proceed, let's discuss the assumptions we have made in our project. Firstly, we have taken into consideration altitude measurement, ensuring accurate and reliable data for the landing gear's operation. Additionally, we have assumed the reliability of our actuators used in the landing gear system to ensure its smooth functionality. Lastly, we have accounted for the proper functioning of the microcontroller, which is a crucial component that controls and coordinates the landing gear's operation. In designing our mechatronic device, we have applied several theories that are fundamental to the field of avionics. One such theory is Kirchhoff's law, which governs the behavior of electric circuits. We have also employed the golden rule, a principle that guides the design of reliable and efficient systems. Furthermore, circuit analysis using methods such as node method has been utilized to analyze and optimize the electrical aspects of our landing gear system. Now, let's move on to the next part of our presentation, the design overview. In this section, we will delve deeper into the research requirements and design considerations that have shaped our landing gear project.
So the design overview, so our design and goals is essentially just to create landing gear with an automatic and a manual mode. So it needs to be able to automatically detect when it's this far off the ground and extend its landing gear, or if it's this far above the ground, the landing gear will retract. Some core concepts in designing this will be logic gates, digital circuits, op amps, and our Boolean algebra. And as a result, we created a functional proof of concept essentially. It would be an alpha stage or maybe even something less than that. We basically created something where it does all the functions that it needs to fulfill its purpose, but I wouldn't go slap it on an airplane and test it out.
For the next part of our presentation, we're going to get into further detail for the logic gate schematics, the truth tables for output 1 and output 2, and the Arduino components we use, such as the microcontroller kit, the echo sensor, stepper motor, and buttons, to name a few.
Okay, so here's our schematic for our overall project. It consists of 5 states. The first state is the state whether it's in the manual or auto mode. Our states B and C are for our manual mode, and state B is whether it's deploying, or state C is if it is retracting. Now our states D and E is our echo sensor. State D is if it is in between 10 and 20 centimeters, it will activate, and state E is if it's within 20 or 30 centimeters, it will activate as well. So it does consist of 2 outputs, and our first output will indicate whether the whole overall system is deploying, and our second output will indicate if the overall system is retracting. So if we look right here at this Boolean expression, we have not A or D, or we have not A and D, or A and B. So what this means is if it is an auto, so if it is an auto and it is in between 10 and 20 centimeters, that this would be true. Or if it's in manual and we press the deploy switch, this will also be true. Alternatively, for our second output, we have if A is in auto and it's in between 20 and 30 centimeters, it will retract. And as well as if it is in manual and we press the switch button for C, it will also retract. So now here's a truth table for our first output. So the way that this works is we have all of our inputs right here, and we have the our Boolean variables, which make up the Boolean expression. So when you see a 1 in this column right here, or a Y1 column, that means that it is true. So I'll show you how to kind of read this with an example of the third row. It says if D is true, so D is equal to 1, and our A naught is equal to 1, which means that A is 0. In English, this means that it is in auto mode, and we are in between 10 and 20 centimeters, that this will be true and it will deploy. You can pick any single one of these, and you can also follow accordingly. So for instance, this one is false, and that is because, right here it says that A is 0, so that means that it is in auto mode. And it says C, so even though that, it says that B right here is also false, so the button is not being pressed, and also we're not in that range, so it will not deploy. So as goes for our second output, which indicates the retracting of the system, we can also pick this second row right here, and we can see that it is in auto mode. It is in auto mode, and our E is equal to 1, which means that we are in between that 20 and 30 centimeter range. And yes, so this A naught is also equal to 1, which indicates that it is in auto mode, that this statement right here is true.
All right, for this slide, I'm going to be going over the CAD SOLIDWORKS design. Essentially, for our first idea, we were going to do a linear actuator, which consisted of this bolt, this nut, and this metal tubing. And this CAD design was basically going to be a housing for this whole linear actuator. And we actually designed it in order to counteract the spin of the whole system, because that is an issue that we ran into. The CAD design with these divots here, or these partitions, would allow the mechanism to extend and retract without spinning. So although we didn't end up using this linear actuator in our final project, I think it was a good learning experience to not only learn CAD for this part, but also to mess around with different ideas to approach the project.
This part that's shown here was our second design in SolidWorks. After the first one that was made, that one was for the linear actuator. This is a different method of extending and retracting the landing gear. So to describe this one, the rectangular portion that you see on the left side, that's going to be where it connects to the stepper motor. This is the part that turns at 90 degrees, which I'll show you later why is important. But the circular part that you see at the other end is where you attach a wheel or anything that's going to connect with the ground. So the way it works is I'll use my hand as a demonstration. This is the part where it connects to the stepper motor, and this is where the wheel is. And basically how it works, very simple, is it turns just like this. So I'll describe it in this situation. The rectangular part is up here while the wheel would be down here. This is a very simplified version of like an extending and retracting of a landing gear compared to the linear actuator. It's just a much simplified version, and we believe it'll just be able to demonstrate it more. It'll be more obvious as to what the part is actually doing, whereas with the linear actuator, we needed a lot of turning from the stepper motor to make it look like it was extending and retracting. So we believe this is just the better option for the project.
So going forward with the Arduino components, in the beginning of the semester, we bought an Elegoo microcontroller kit that had many types of sensors and components. The first component for our landing gear was to use the echo sensor to detect at what height we want our landing gear to deploy or retract. And this was our this would be our automatic mode. Then using the Arduino IDE, we coded the stepper motor to deploy when the sensor detected between 10 to 20 centimeters and to retract when it was 20 to 30 centimeters. Then we used 3 buttons, one to switch between auto and manual, one to deploy, and one to retract. Then we used the LED lights to tell us what's going on with our design. White if the system is on automatic or manual. Red means the sensor detects 10 to 20 centimeters. Yellow means 20 to 30 centimeters. Blue, deploy, and green, retract. And then lastly, we use 3 types of logic gates, and, or, an inverter. And this is what our final design looks like. You can see the Arduinos right here, the LED lights, the echo sensor, the buttons, the resistors, and the logic gates, and the stepper motor. And this is what it looks like all hooked up. We try to solder everything to try to make everything look a little neater and make a housing for it. But unfortunately, we did not have enough time, so this is what it looks like currently. You can see the components are soldered onto the perma board similar to the breadboard used on the last slide. So the resistors, logic gates, and the sensor, and the LED lights, and the buttons right here.
As for the conclusion, the requirements have met, which is the auto and manual mode. For the auto mode, when it's on, the landing gear, it extends and it retracts if it's X meters above the ground. When the auto is off, the user extends or retracts the landing gear. For the LEDs, each LED shows something. So the red light indicates that the landing gear is 10 to 20 centimeters from the ground. Yellow light, it indicates the landing gear is 20 to 30 centimeters from the ground. Blue light shows that it's deployed. Green light, it shows that it's retracted. White light, it shows that the landing gear is in auto mode. We also used 1 sensor, 1 actuator, 1 microcontroller, and 3 logic ICs. For the logic IC and inverter were used, 1 ultrasonic sensor, and also 1 stepper motor. It was used as an actuator.